So, in the previous class we had studied the QPSK modulation scheme and we had derived the probability of message or symbol error. Now, what we are interested is in the derivation of probability of bit error, and we will do that in this class. We had derived the probability of the symbol error to be as follows. So, given this we can find out the probability of symbol error. Now, even though a message error has been made, it does not mean that a specific bit is in error. We took an example that if we transmit the message M1 which is 00 bits and we decide in favor of M2 which is 0 1, then in this case the second bit goes in error. So, to determine the bit error probability, it is necessary to distinguish between different message errors. Now, again because of the symmetry, it is sufficient to consider only a specific message, say let us say M1. Then the different errors we will evaluate. So, when we have got M1, this could be decoded as M2, in which case the second bit will be in error. If M1 gets decoded as M3, then both the bits will go in error, and if M1 gets decoded as M4, then only the first bit is in error. So, the different error probabilities which we will get can be computed very easily. So, probability that we decode as M2 given M1 implies that the first bit should be correct, and that would be given by this expression, and this is the probability that the second bit goes in error. The calculation of this probabilities is very clear if you look at the signal constellation diagram which we had studied in the previous class. So, from looking at the signal constellation diagram, we can immediately write this probability of decoding as M2 given M1. Similarly, for the probability of decoding M1 as M3 would be given by this expression, because we want both the bits to go in error, and probability of decoding as M4 given M1 would be that the first bit goes in error, which is equal to this, and the second bit received is correct. So, it would be this value. When the message errors of M2 or M4 occurs, given that M1 was transmitted, then the chosen bit is in error with a probability of 0.5, where we presume that one of the two bits is chosen at random, that is with a probability of 0.5. Now, when the message error of M3 occurs, then the chosen bit is certain to be in error, therefore, it has a probability of 1. With this philosophy, we can write the bit error probability as follows. This is the probability given M1 has been transmitted decoding as M2, and you multiply this by 0.5 because the chosen bit is in error with a probability of 0.5. Okay. And similarly, for the case of M4 being decoded as M1, and in the case of M3 given M1, you multiply this by 1. Okay. So, and then if we use these expressions, it is easy to see that this will simplify to this expression out here. So, from the above derivation, it is clear that the way each information bit pair is mapped to a message or signal influences the bit error probability. Specifically, the mapping determines how the probabilities 0.5, 0.5 and 1 are associated with the 3 error probabilities here, correct. And recognize that probability of M3 given M1 is less than probability of M2 given M1, which is equal to same as probability of M4 given M1. So, what this implies that it is desirable to associate the probability 1 with probability of M3 given M1 in order to minimize the overall bit error probability. So, what this implies that the signals S1 and S3, which are separated by the largest Euclidean distance, should be mapped to the bit pairs that differ in both bits. So, equivalently, the signals that are closest to each other, that is the nearest neighbor, should be mapped to the bit pairs that differ in only one bit, and such a mapping is called a gray mapping. And this, the way we carried out the mapping is a gray mapping. Now, for a fair comparison with the error performance of the binary modulation schemes which we have studied earlier, it is necessary that we express the probability of the bit error in terms of the average energy per bit, and this can be easily calculated as follows. Now, QPSK signal carries 2 bits of information, and the energy of each signal is equal to A squared multiplied by TB. So, the average energy per bit is equal to E by 2, which is equal to A squared TB by 2. Therefore, we can write the probability of bit error in terms of the energy of the signal. This is equal to So, what this expression shows that the probability of bit error is the same as that of the binary PSK. So, this clearly demonstrates the advantage of QPSK over BPSK. With QPSK modulation, the bit rate can be double without requiring any additional bandwidth or sacrificing the error performance. Interpreted differently, to deliver the same transmission rate at the same bit error performance, using QPSK reduces the transmission bandwidth to half of that required by BPSK. Now, we will look at the alternative implementation of the QPSK modulation, and we will do this with the help of an example. This alternate representation of QPSK helps us to implement the QPSK easily in practical applications, and the principal operation is as follows. So, given a bit sequence 10 11 00 101, the information bit stream is first converted to a non-return to 0 waveform with plus minus 1 levels. So, these are levels are plus 1 and minus 1, and this waveform we call it as alpha t. This waveform alpha t is then demultiplexed into even and odd waveforms of bit streams, which we denote as alpha it and alpha qt. So, I and q here are mnemonics for in phase and quadrature respectively. So, the individual bits in each stream occupy the duration of 2b seconds, which we call it as Ts second, and each of this modulate the in phase carrier and quadrature carrier. So, in this case the in phase carrier would be a cos 2 pi fct, and in this case the quadrature carrier would be a sin 2 pi fct. So, it is easy to see this. I take the first bit alpha 0 and it remains there over the period 2b. Then we take alpha 2 and that also remains over 2 tb duration. And for alpha qt, we pick up the odd bits from here, alpha 1, alpha 3, alpha 5, alpha 7, and get this waveform for alpha qt. So, each of this even and odd bits are picked up from the original bit stream and they are extended over a duration of 2 tb. So, the QPSK modulator will look something like this. I have my alpha t, the input, and then it gets demultiplexed into 2 bit streams. This is the in phase and this is the quadrature bit stream, and each of this bit stream get modulated. This gets modulated by cos 2 pi fct, this gets modulated by sin 2 pi fct, and st is the QPSK signal which is generated. So, the transmitted signal is as follows. In phase bit stream or in phase waveform modulates cos 2 pi fct. Quadrature waveform or quadrature bit stream modulates the carrier a sin 2 pi fct, and this can be rewritten as alpha qt divided by alpha it. So, this can be, this values are plus minus 1. So, this I can write is as root 2 a cos of 2 pi f c t minus theta t, where the phase theta t is determined as follows. So, it is equal to pi by 4 if alpha I is equal to plus 1, alpha q is equal to plus 1, and that will correspond to bits being 1 1, minus pi by 4 if alpha is 1, alpha q is minus 1, this corresponds to bits 1 0, 3 pi by 4 if alpha I is equal to minus 1, alpha q is plus 1, corresponds to bit 0 1, and finally theta t is equal to minus 3 pi by 4 if alpha I is equal to minus 1, alpha q is equal to minus 1, and bits are 0 0. So, using this alpha t and demultiplexing, we generate, after modulation, we get this waveform. So, alpha it a cos 2 pi f c t, alpha qt a sin 2 pi f c t, and then it is the summation of this 2 is your qpsk signal which we have generated. So, now from this equation it is clear that the transmitted signal is a QPSK signal and depends upon the specific even and odd quadrature bits which select the phase theta t of the sinusoidal carrier root 2 a cos 2 pi f c t minus theta t. So, you get 4 signals out of this for different values of alpha q t and alpha I t, and this can be represented by the following 2 orthonormal basis signals. Phi 1 t is this signal and phi 2 t is given by this signal, and using these 2 signals basically for representation we can get the signal constellation for QPS signals as shown in this figure. So, these are the 4 signals which we get. The phase of each signal is relative to this phi 1 t axis. So, this signal out here is at pi by 4, this signal is minus pi by 4, this is 3 pi by 4 and this is minus 3 pi by 4. Okay. So, now we will calculate the minimum error probability receiver for the implementation of the QPSK which we have discussed. Now, note that the even bit stream, that is your in phase, and the odd bit stream which is your quadrature, both this can be treated separately since the alpha it bit stream of waveform does not have any component along phi 2 t basis signal, and similarly alpha q t bit stream of waveform does not have any component along the orthonormal basis signal phi 1 t. So, what this implies that QPSK signal can be considered to consist of 2 separate non interfering BPSK signals. So, the signal space diagram would be as shown here. This is for the in phase part and this is for the quadrature part, where this signals SIT, S2T and here S1QT and S2QT are as defined on this slide. This is easy to realize because remember that your alpha IT is a polar waveform which modulates cos 2 pi FCT and XQT is a polar waveform which modulates A sin 2 pi FCT. So, for this the basis signal in the in phase branch would be this and the basis signals for the quadrature branch would be as written on this slide. Right. So, for this case now the receiver would look as shown on in this slide. We get the received signal and you project them on phi 1t and phi 2t. You get the projections R1 and R2. You take the independent decisions. So, this will give the even stream and this will give the odd bit stream and you multiplex them to get the final waveform alpha t. So, let us calculate the probability of error for any one of this because it is going to be the same. So, if we know the distance here, so the probability of error would be given by the following expression d12 by 2 divided by root of n italic n by 2. This is equal to, look at this distance, this is twice of this. So, substituting there we will get root of a square Ts by italic n. Now, energy of the QPSK signal we know is equal to a squared Ts. So, the energy per bit is equal to E by 2, which is a squared Ts by 2. So, from this we get the probability of error to be equal to q times root of 2 EB by italic n. Substitute here and this you get this quantity. So, this is indeed the same as derived earlier. So, finally, we have to calculate the power spectral density of the QPSK signal. Now, realize that QPSK signal is a sum of two BPSK signal and there is a statistical independence of the even and the odd bit streams, which are the two BPSK signal that make up the QPSK signal, and since they are uncorrelated, it follows that the power spectral density of the QPS signal is twice the power spectral density of each of the BPSK signal. It is just scaled by 2 and with Ts substituted for TB. QPSK signals phase could change by plus minus 90 degrees or plus minus 180 degrees. Now, this can be of particular concern when QPSK signal is subjected to filtering before detection. Specifically, the 180 degree and 90 degree shifts in the carrier phase can result in changes in the carrier's amplitude, that is QPSK signals envelope, and consequently affecting the probability of symbol errors on detection. There is a form of QPSK known as offset or staggered QPSK, which mitigates this problem of 180 degrees phase shift, and this we will study next time. Thank you.